Concepts of deductive reasoning. This comes from the supplemental text, sections 1.7 and 1.8. Now, don't be alarmed if after this presentation you're not totally comfortable with what's going on. We will try to solidify this in class tomorrow, and this is really, deductive reasoning is a work in progress. It is something we'll be talking about throughout the year. The science of deduction is the foundation for geometric proof. So deductive reasoning, or using deduction, is using a series of logical steps to show something is true, to get from one point to another. So geometry is built around deduction. Deductive structure involves four basic elements. The first element are undefined terms. Undefined terms are really anything that is given to us. Things like points and lines we talked about as being undefined terms in geometry because you can describe them, but you can't really come up with a true definition for them. But when we're looking at proofs, really anything that's given to us, it could be a statement of that we're accepting as true. It could be a diagram, or anything that is given to us we'll consider undefined terms, and that's part of our deductive structure. And it's usually a starting point for us in a proof. We will use postulates when we're proving things to be true. Now, a postulate is just an assumption in geometry that we assume to be true. It's not something that can be proven. So an example of a postulate we have seen already is like the segment addition postulate or the angle addition postulate. Those are things that we can visualize and we can see them, and it's kind of logical, but we can't really prove that that segment addition works, except for maybe showing how it works. We'll also use definitions when we're proving things in geometry. So in a definition, it's pretty obvious. It states the meaning of a term or an idea. We're going to talk a little bit more about definitions in the coming slides. And finally, we will use theorems in our geometric proofs. And we haven't seen too many theorems as of yet, but I assure you we will see hundreds before the end of the year. And a theorem is a mathematical statement that can be proved. So unlike a postulate, a theorem we can actually prove, often using deduction. Many of them we will just accept, but if we wanted to go ahead and prove them, we could. We haven't seen too many theorems yet, but I think we did see the right angle theorem the other day. So the right angle theorem is the one that says that all right angles are congruent. So something that is unique about definitions is that they are what we call reversible. So for example, the definition of the midpoint of a segment. If a point is the midpoint of a segment, then the point divides the segment into two congruent segments. This if-then structure is something we're going to see a lot of, this if-then. So the portion of the statement that comes after the if, in this case, a point is the midpoint of a segment. So if a point is the midpoint of a segment, we call that the hypothesis. The portion of the statement that comes after the then the point divides the segment into two congruent segments, we call that the conclusion. So you'll see a lot of these if-then statements in geometry. If some hypothesis, then we're going to draw this conclusion. So what we're saying about definitions is that definitions are reversible, meaning we can interchange, or we can change the hypothesis with the conclusion. So we can state with a definition, if a point divides a segment into two congruent segments, then the point is the midpoint of the segment. Notice, we took the conclusion and made it the hypothesis, and we took the original hypothesis and made it the conclusion. So a definition is something that is always reversible. That is not the case for postulates and theorems. So while some postulates and theorems can be reversed, not all of them can be. Consider this following theorem. If two angles are right angles, then they are congruent. Notice that if-then structure again. So two angles are right angles being our hypothesis, then they are congruent being our conclusion. So that's true, right? If two angles are right angles, then they're congruent because we know that all right angles are congruent. Can we reverse this statement and say that if two angles are congruent, then they are right angles? Is that a true statement? No, because we can have angles that are not right angles that are congruent, right? We can have two 30-degree angles and they're congruent, but they're not right angles. So notice that this theorem, called the right angle theorem, is not reversible. So just to formalize here, we have all of these definitions and these theorems we've seen thus far have been written in the form of what we call a conditional statement. If P, then Q. Again, P being that hypothesis, and Q being the conclusion. A short version of this is P and that double arrow Q. So if P, then Q, or P implies Q is another way to say this. The converse of a conditional statement is the reverse. So if Q, then P. So keep in mind those definitions, we were writing a definition, we were writing it as a conditional statement, and then when we reversed it, we wrote its converse. So we used the original conclusion as our new hypothesis. I told you this might get a little confusing. We're not done yet. So let's take an example. Write the converse of each statement and then tell whether it is true. If you're at least 16 years old, then you can get a driving permit. And let's assume we're in the state of Connecticut. I should have indicated that. So if you are at least 16 years old in the state of Connecticut, then you can get a driving permit. So the converse of this statement, again, will flip-flop the hypothesis and the conclusion. If you can get a driving permit, then you are at least 16 years old. Again, assuming we're in Connecticut. So is the converse true? Yes, it is. Because if you can get a driving permit in the state of Connecticut, then you must be at least 16 years old. So the converse of this statement is indeed true. Let's take another example. If each side of a triangle has a length of 10, then the triangle's perimeter is 30. So that's true. A triangle has 3 sides. If each side is a length of 10, 10 plus 10 plus 10 is 30. But what is the converse of this statement? The converse says, if a triangle's perimeter is 30, then each side of the triangle has a length of 10. So is that true? Hopefully you said no, because can't we have a triangle with different side lengths that also adds up to 30? For example, maybe 12, 12, and 6, or 10, 15, and 5, right? So there are a variety of different side lengths of a triangle that we could have and still have a perimeter of 30. Negation. The negation of a statement P is the statement not P. So for example, if we say it is raining, the negation of it is not raining. It's not really rocket science here. So we use the symbol tilde, that little squiggly line, to indicate not. So not P is written tilde P. It's just an abbreviation. So why is negation important to us? Negation is important because it's going to come into play when we talk about other kinds of statements that are associated with conditional statements. So every conditional statement that we can write, the if P then Q type of statement, has three other statements associated with it. We've already seen the converse. That's when we interchange the hypothesis and the conclusion. So if the conditional is if P then Q, the converse is if Q then P. The inverse inverts the original statement. So the inverse is if not P, then not Q. And then finally, the contrapositive says if not Q, then not P. Hopefully I'm not confusing you guys too much. Let's look at an example. Let's look at this example. Write the converse, inverse, and contrapositive of the following statement and state whether each is true. So the one thing about converses, inverses, and contrapositives is you can have a conditional statement that is true, but the other three statements may or may not be true depending on what it is that we're talking about. So our original statement is if you live in Toronto, then you live in Canada. So that is true because Toronto is a city in Canada. So our original statement, if you live in Toronto, then you live in Canada, we already said was true. Let's look at the converse of that statement. The converse was when we interchange the hypothesis and conclusion. So if you live in Canada, then you live in Toronto. Well, it's not necessarily true because we can live in Canada and live in another city in Canada like Ottawa or Quebec or Montreal. So the converse is false. Now how about the inverse? The inverse involves the negation of the original statement. So if you don't live in Toronto, then you don't live in Canada. Well, this is kind of similar to the converse. This is saying that if we don't live in Toronto, then we can't live in Canada, but that's not necessarily true because, again, we can live in another city in Canada, and that's not Toronto, and still be in Canada. So the inverse is also false. Now for the contrapositive. If you don't live in Canada, then you don't live in Toronto. Well, assuming there are no other cities in the world called Toronto, we can say that this is true. Because if we're not in the country of Canada, we can't be living in Toronto. Okay, so when the science of deduction involves a chain of reasoning, when we prove something in geometry, we're going to be using a series of logical steps. We can't get from one point to another if it doesn't make sense, and this involves what we call a chain of reasoning. So a series of conditional statements that's connected is called this chain of reasoning, and it takes a form of this. So if P implies Q and Q implies R, then P must imply R. You see that? So if P then Q and Q then R, then P must imply R. And this could have more than three statements here. I mean, we could easily say if P implies Q and Q implies R and R implies S and S implies U, then P must imply U. Okay, so we can have as many steps in there as we want. But the idea here is that we can't get from P to Q, Q to R, or from P to R without that intermediate step there. We have every single step has to make sense. We can't take what we might call a leap of faith. So we're going to end on just a fun example involving the chain of reasoning. And we'll talk about the answer to this tomorrow in class. Use the chain of reasoning to draw a conclusion from the following statements. If gremlins grow grapes, then elves eat earthworms. If trolls don't tell tales, then wizards weave willows. If trolls tell tales, then elves don't eat earthworms. So think about that tonight, and we'll talk about that more in class tomorrow. See you then.